projects. In this video, we are going to explain about the project, which is CMTSNN, a deep learning model for multi-class classification of abnormal and encrypted traffic of Internet of Things. Introduction of the project. The rapid evolution of 5G mobile communication technology has ushered in the era of Internet of Things, bringing unprecedented connectivity to devices worldwide. As of June 2022, the global IoT connections have surged to 14.4 billion, spanning across various industries such as healthcare, manufacturing, and power grids. With the proliferation of IoT devices and the surge in encrypted abnormal traffic, ensuring the cybersecurity of IoT systems has become a paramount concern. The complexity of identifying, classifying, and securing the vast amount of data flowing through these networks poses significant challenges that demand innovative solutions. Recognizing the critical need for a reliable IoT architecture, the project focuses on developing advanced defense mechanisms and detection systems. Key cybersecurity measures, including firewalls, antivirus applications, and intrusion detection systems, are proposed and implemented to safeguard IoT devices from external threats. Despite the existing methods for network intrusion detection, current approaches face challenges such as the adaptability to encrypted traffic and the impact of data imbalance on classification performance. Traditional methods, including port based and payload inspection techniques, have the limitations that necessitate more sophisticated and efficient solutions. In response to the identified challenges, the project introduces a novel deep learning model, that is cost matrix time space neural network, which is CMTSNN. This model addresses the issues like accurately classifying encrypted abnormal traffic, ensuring effective feature extraction. The CMTSNN integrates bidirectional long short-term memory and one-dimensional convolutional network for robust feature extraction and employs a cost penalty matrix to enhance the classification performance, particularly for minority class traffic in the IoT. Objective of the project. The primary objective of this project is to develop and implement a multi-class classification deep learning model known as cost matrix time space neural network with the aim of enhancing the detection and classification accuracy of abnormal and encrypted traffic within the IoT Internet of Things. The overarching aim of this initiative is to address the growing cybersecurity challenges posed by increasing diversity of IoT devices, coupled with proliferation of malicious programs and the widespread adoption of encrypted technology. The project seeks to specifically identify and classify abnormal encrypted traffic, establishing this as a fundamental premise for bolstering IoT cybersecurity. As an essential aspect of the project's focus is to optimize dataset processing methods. The aim is to overcome existing limitations associated with simplistic dataset handling, ensuring a more sophisticated approach that aligns with the intricacies of diverse IoT devices and malicious program behaviors. With a focus on feature extraction in the network flow analysis, the core aim is to enhance the robustness of this process. The project aims to extract both time series and spatial features, ensuring a comprehensive and resilient approach that contributes to the accurate identification of abnormal and encrypted traffic patterns. The integral objective of the project is to address the challenge of the data imbalance with IoT datasets. This involves the implementation of cost penalty matrix during the training process, strategically designed to improve the classification accuracy of minority categories. The ultimate goal is to enhance the overall multi-classification performance of the proposed CMTSSN model. To implement this project, we need software and hardware requirements. Software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. This step involves bringing the essential libraries and packages into the project environment. We have imported pandas for data manipulation, NumPy for numerical operations, Seaborn and Matplotlib for visualization, TensorFlow and Keras for deep learning, and Flask for web development. The next step is exploring the dataset. In this step, BOT IoT and NFTON IoT are explored to understand their structure and contents. These exploration lays the groundwork for subsequent data processing and analysis. Data processing. This involves creating pandas data frames to efficiently manipulate and analyze the data sets. Additionally, conversion of the data into keras, which is compatible format of machine learning tasks. Unnecessary or redundant columns are removed during this step to streamline the dataset for further analysis. Visualization using Seaborn and Matplotlib. This step employs Seaborn and Matplotlib for data visualization. Plots and charts are created to reveal insights into the data distribution, relationships, and patterns. Label encoding using label encoder. This step involves converting categorical variables into numerical format using label encoding. This numerical representation is necessary for machine learning algorithms that require numerical input. Feature selection. Feature selection is performed using select percentile method with mutual information classification. This step identifies and retains the most informative features for subsequent classification tasks. Splitting the data into train and test. This step encompasses the division of the dataset into training and testing sets. The training set is used to train the machine learning model, while the testing set is reserved for evaluating the model's performance on unseen data. Building the model. In this step, deep learning models are defined and configured. Here, we select the neural network specifying layers and configuring parameters are made in this phase. Training the model. This step involves utilizing the training data set to train the machine learning model. During training, the model learns patterns and relationships within the data, preparing it for subsequent predictions. Flask framework with SQLite for sign up and sign. The implementation of Flask web framework is undertaken in this step. Additionally, SQLite, a lightweight relational database, is integrated to provide functionality for user sign up and sign in within the web application. User gives input as feature values. This step allows users to input feature values through the front end of the web application, facilitating user interaction with the machine learning model. The given input is pre-processed. The user inputted feature values undergo pre-processing to ensure compatibility with the format expected by the trained model. This step is crucial to prepare the input for accurate predictions. Trained model is used for prediction. Utilizing the pre-processed user input, this step involves applying the previously trained machine learning model to make predictions. Final outcome is displayed through frontend. The final step involves presenting the prediction outcome to the user through the front end of the web application, completing the interactive loop between user input and model prediction and the result to display. Now we will know what are the algorithms used in the project. Coming to CNN, which is convolutional neural network, it is a class of deep neural networks designed specifically for processing grid-like data such as images. It utilizes convolutional layers to automatically learn hierarchical features from the input data, allowing it to capture patterns and spatial relationships effectively. While CNNs are traditionally associated with the image data, they can also be adapted for structured grid-like data, making them suitable for tasks where spatial relationships are important, such as sequential data or time series. Coming to DNN, which is deep neural network, it is a neural network with multiple hidden layers between the input and output layers. DNNs are capable of learning complex hierarchical representations of the data, enabling them to capture intricate relationships within input features. The next one is bi-LSTM with CNN, which is bidirectional LSTM with convolutional neural network. This hybrid model combines the strength of bidirectional long short-term memory, which is bi-LSTM, and convolutional neural network, which is CNN. Bi-LSTM captures sequential dependencies bidirectionally, while CNN focuses on spatial feature extraction, making it effective for tasks involving both temporal and spatial patterns. The next one is CNN with bi-LSTM, which is convolutional neural network with bi-LSTM. Similar to the previous combination, but with the order reversed, the model first processes spatial features with CNN and then captures sequential dependencies using bidirectional LSTM. It is effective when the spatial features play a primary role in the initial stages of data processing, followed by the need to capture temporal dependencies within sequences. The next one is CM by LSTM, which is cost matrix bidirectional LSTM. Cost matrix is a square matrix where each entry represents the cost or penalty associated with misclassifying a particular class. In the context of machine learning classification, it is used during the training phase to assign different costs to different types of classification errors. Coming to bi-LSTM, which is bidirectional LSTM, it is a type of recurrent neural network architecture, which is RNN architecture. Unlike traditional LSTMs, which processes sequences from the past to future, bi-LSTM processes sequences in both directions, which is past to future and future to past. This bidirectional processing enables the model to capture context, and dependencies from both preceding and succeeding elements in the sequence. The next one is CMTNN, which is cost matrix time series neural network. A cost matrix is a square matrix used in machine learning classification tasks to assign different costs or penalties for misclassifying instances or different classes. Coming to time series neural network, it is a neural network architecture specifically designed for handling time series data. It is tailored to capture temporal dependencies and patterns in sequential data, making it suitable for applications such as forecasting, anomaly detection, or the classification in time series datasets. CMTNN suggests a neural network tailored for time series data. The details involve specific architectures or the techniques designed to capture temporal dependencies in the sequential data effectively. It is specialized for tasks involving time series analysis where understanding and capturing temporal patterns are crucial for accurate predictions. As an extension, we applied an hybrid method, combining the predictions of multiple individual models to produce a more robust and accurate final prediction. As an extension, we built the front end using Flash framework for user testing with the user authentication. We have used accuracy, precision, recall, and F1 score, which are the performance metrics to evaluate this project. So here we have performance comparison graphs for all those metrics for the dataset, which is BOT IoT. This is the accuracy comparison graph. Here on x-axis, we have accuracy score for each algorithm, and on y-axis, we have algorithm names. Similarly, we will have for other graphs also. Accuracy is a measure of the overall correctness of the model. It calculates the ratio of correctly predicted instances to the total number of instances. This is the precision score comparison graph. It is the ratio of correctly predicted positive observations to the total predicted positives. It evaluates the accuracy of positive predictions. This is the recall score comparison graph. Recall measures the ability of the model to capture all relevant instances. It is the ratio of correctly predicted positive observations to the total actual positives. This is the F1 score comparison graph. F1 score is the harmonic mean of precision and recall. It provides a balance between precision and recall, especially when there is an imbalance in the class distribution. Here we have performance comparison graphs for the dataset, which is TON IoT. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the dataset folder. Here we have two datasets which are BOT IoT and NFTON IoT. We use these datasets for training the algorithms. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the model file, which contains the algorithm information and that will be loaded into the project code during runtime. These are the two IPYNB files, which are the Jupyter Notebook files, which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the sign up file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. This will change current directory to the code folder's path. Here we need to type the command python space app.py and click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. This is the local host and this 5000 is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link. First, we need to click on that and enter all the sign up details if we are signing up newly. I have already signed up and I have an account in it, so we'll directly log in. For that, click on login. Here we need to provide our credentials to login, which are the username and the password. So I'm giving my username and the password. Now click on login. We have logged in successfully and we are redirected to prediction page. Here you can see the parameters which are need to be entered. Based on the given parameters, we will get the prediction whether attack is detected or not. Before entering the parameters, we will understand them. So the first one is L4 source port, which is layer 4 source port. This parameter indicates the source port number at the transport layer of the network protocol stack. Here layer is a layer 4. The source port is a 16-bit number used to identify the application or the process sending the network traffic. Next one is layer 4 destination port. Similar to source port, the destination port is a 16-bit number indicating the port at the destination application or the process. It is a part of transportation layer 4 information in the network traffic. Protocol. Protocol parameter identifies a network protocol used for communication. Coming to layer 7 proto, it is layer 7 protocol refers to the application layer protocol in the OSI model. In bytes, in bytes is a parameter representing the total number of incoming bytes in the network flow. It measures the amount of the data received during the specific period. The next one is out bytes. Out bytes, similar to in bytes, this parameter indicates the total number of outgoing bytes in a network flow. It measures the amount of the data transmitted during the specific period. Next one is in packets, which is inbound packets. Inbound packets represent the total number of packets received in a network flow during the specific duration. Out packets is the outbound packets. Outbound packets indicate the total number of packets transmitted in a network flow during the specified duration. Coming to TCP flags, in the context of TCP traffic, TCP flags represent control bits in the TCP header. These bits include flags such as SYN, ACK, FIN, etc., providing information about the state of the TCP connection. TCP is Transmission Control Protocol. The last one is flow duration MS, which is flow duration in milliseconds. Flow duration represents the time duration of the network flow in milliseconds. It indicates the time between the start and the end of the observed flow. As we have understood all the parameters, we will enter them. So, layer 4 source port number is 51722. Layer 4 destination port is 80. Protocol value is 6. Layer 7 proto is 7. In bytes is 458. Out bytes are 2203. In packets are 5. Out packets are 6. TCP flags are 27. Flow duration in milliseconds is 562. Now we will click on predict. Here we got the prediction as there is an attack detected and the attack type is zeros. Now we will enter the parameters again but with different values. Click on prediction. Layer 4 source port number is 821272. Layer 4 destination port is 52951. Protocol is 6. Layer 7 proto is 7. In bytes are 795. Out bytes are 4374. In packets are 10. Out packets are 12. TCP flags are 27. Flow duration in milliseconds is 750. Now click on predict. Here we got the prediction as there is no attack detected and it is normal. Now click on sign out. In this way, if we enter the parameters to the system based on the given parameters, we will get the prediction whether attack is detected. Conclusion of the project. The project has successfully addressed the cybersecurity challenges posed by the increasing types and the number of Internet of Things devices. The implemented algorithms and the model, including CMTNN and CM by LSTM, demonstrate robust capabilities in detecting and mitigating abnormal and encrypted traffic, ensuring the security of IoT ecosystems. The extension model exhibit noteworthy success by achieving high accuracy, showing their effectiveness in surpassing baseline performance and enhancing the overall reliability of the system. The project's robust cybersecurity measures and the versatile model empower stakeholders in the Internet of Things ecosystem, providing a reliable defense against potential threats. This includes benefiting industries relying on IoT technologies, researchers exploring IoT security, and practitioners seeking effective solutions for securing IoT networks. The integration of the Flask framework with SQLite for sign up and sign in, coupled with the ability of the users to input feature values, and brings a practical and user friendly dimension to the project. This front end interaction enhances project's applicability, making it accessible for real world scenarios.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.